It's more convenient, I believe. Okay, so I will start, okay, with today's new topic. So today we will discuss a new topic. It's about dimensionality reduction, okay. And you remember last class we discussed the curves of dimension. Is it, you remember that issue? Is it, it's because of too many features, is it? Especially with like image file. Later on we will see example. Is it because for image, if even it's the pixel is very low, is it? But for a very simple image, then because we need to convert it to number of rows of pixels times number of columns of pixels, is we need to convert this multiplication to all row to all columns for the features. So that's, so even though with a 32 by 32, it's much larger. So that's why we needed to discuss some way to do dimensionality reduction. Okay, so let's take a look what the concept is here. And previously we learned the feature selection. And I'm not sure if you still remember that there are, do you remember the approach that we learned about feature selection? You remember you can use the what feature importance, is it? You remember for random forest, you have that attribute. So you can make use of this feature importance, is it? And it lists the percentage, is it? All of the features percentage, you remember, we have something like this, is it? And to all the way maybe 0, 0, 1 something, is it? And then based on this feature important, and then you can pick certain number of features, is it? And retrain the model and to see its performance, is it? So feature importance is one way. And I'm not sure if you still remember the other concept that we discussed, regularization. Do you still remember the regularization? There are two kinds of regularization. Who still remembers? Air what? Both with air. Do you still remember the two regularization? L1 regularization, is it? And L2,
Logistic and linear.
yeah. So L1 regularization and L2 regularization, is it? Generally speaking, L2 regularization can help to improve performance with what? Deal with overfitting issue, is it? Because it's through what? It's through penalize, is it? Penalize weights. So that's how it get to the goal, is it? And L1 regularization, do you remember? It's not, yes, I heard someone mention it's linear, is it? It doesn't involve the square of weight. It's just absolute, sum of absolute of weights, is it? So it can lead to what? We mentioned sparse features, is it? So it can lead features to 0, certain features to 0 value, is it? And because if the weight is 0, then you can filter it out, is it? So L1 regularization can also help in certain way with feature selection, okay? So that's a feature selection that we already learned. And over here, there's another concept. It's called feature extraction, okay? Feature extraction. So feature extraction is to do, it's to transform or project data onto a new feature space. Okay, so here it involves transform or project data onto new feature space. Okay, so here it says in the context of dimensionality reduction, okay, feature extraction can be understood as an approach to data compression, okay, with the goal of maintaining most relevant information. Okay, so in some way it can also achieve the goal, kind of like data compression. So later on, when we take a look at our example, that MNIST example, that you will see it can get, you can have the original image that, and if you conduct dimensionality reduction, that it can be lead to, it's kind of like also achieve kind of data compressions goal. Okay, so we will see that feature. And here it says feature extraction, because it can reduce dimensionality, is it? So one of its advantages to what? Improve storage space, is it? And the computational efficiency of the learning algorithm. Okay, it says it can also prove the predictive performance, okay, by reduce the curse of dimensionality. Is it? So last class we learned that. It says especially when we're working with non-regularized model, is it? And the regularized model, remember, like a gradient descent, is that you can regularize it, is it? And here it says non-regularized model, is it? Like k nearest neighbors, is it? Okay, so this is the concept of feature selection versus feature extraction. Okay, be careful. So here, extraction means the goal you want to achieve is to achieve dimensionality reduction. Okay, so this is the concept part. So next, let's see. Okay, then here it says regarding feature extraction. Okay, so here we discuss feature extraction. How do we achieve dimensionality reduction? Is it? So there are a couple of approaches. Okay, so just be careful. Okay, here we said dimensionality reduction means you are going to project your original data onto new feature space. New feature space. But this new feature space, the dimensionality is going to be reduced compared with the original one. So you have fewer features, kind of. Okay. But the feature is not like a feature selection, because feature selection is you filter out features. Okay, and here it's you're going to project your data into new feature space. Okay, so it's not you just to kick out some features. So it's a different concept. Okay, and the approach here to list, why is you may see this a lot. Okay, for machine learning, PCA. Okay, it's called principal component analysis. Okay, PCA, and it's for unsupervised data compression. Okay, mostly it's for feature extraction and dimensionality reduction. Okay, the second way is called linear discriminative analysis, so LDA, so PCA versus LDA. And LDA is a supervised dimensionality reduction technique, okay? And it's to maximize classification, okay? So this is pretty good for classification. And the other one is called KPCA, okay, KPCA. So we have PCA, is it? But we will also see for non-linear dimensionality reduction, then we can borrow the concept of kernel. Do you remember where else we learned the word kernel? Do you remember previously in which unit we learned? kernel. Do you remember to deal with nonlinear classification? You remember? Who remember that? It's what? Yeah, someone sent a chat. It's for, you remember? We learned SVM. You remember? Over there is that we discussed kernel SVM. Okay. Okay, so just remember. So here the kernel concept is similar. Okay, so it's just a mathematics approach to deal with transformation. Okay, because if we use this kernel concept, it can simplify a lot of work. Okay, so that's regarding PCA, LDA, KPCA, okay, the three approach under dimensionality reduction, okay. Okay, then next, let's see, okay. It says unsupervised dimensionality reduction via, so here it's discuss PCA, okay, PCA. And the PCA says it's basically some statistical procedure. And it uses, we will say it's orthogonal transformation. Okay. And here orthogonal means they are going to be perpendicular, okay, with each other. So you're going to use orthogonal transformation to convert a set of observations. And here it's related variables into a set of values that's going to be linear unrelated. Okay, so those linear unrelated variables, then we call them principal components. Okay, so that's the concept here. Okay. And like I previously also explained, is that for feature selection, you're going to maintain the original features, is it? But here you are going to apply some transformation. Okay, feature selection doesn't involve transformation, but here it involves the transformation, then project into new feature space. Okay, new feature space. Okay, so that's the concept here about PCA. So let's see. So here it gave us some diagram, so we can kind of see the idea about PCA, is it? So this shows a original feature space. So X, is it original X1, X2, is it original feature space, is it? And from this diagram, you can also kind of see, is it? So you see, if you have these two new coordinates, as we call them principal component, as a principal component. So if you transform, as a kind of you rotate the coordinate system into certain angles, is that kind of like that concept. And then if you project the data, then you can kind of save a lot of work. Okay, so that's the idea about PCA. So the basic concept. Okay, so it's a principal component analysis. So it's kind of you transform, is it, the coordinate system, and then your data will be reprojected, is it? So this are the two new features, is it? It transform, it's not as original. These are the two new features, is it? But over here, you transformed the features, is it? So that's the concept, okay. Okay, then let's see next. The main step to do the PCA, we will see in our example, okay. Behind this, yeah, the major idea behind the principle, as said, PCA is to identify patterns, okay, in data based on correlation features. Okay, so later on we will see how we express this correlation, how do we transform basically, so we use some math concept, okay. And here it says, is to find the directions of maximum variance in high dimensional feature space. Okay, so so here is to find what? To find maximum variance of the directions. So here is the concept. And the variance measures what? Measures data spread out. Is it? Measures data spread out. Is it? So you want to find the most spread out ones, directions. Is it? So that's the concept, okay. And then principal components basically just some orthogonal axis for the new feature space, okay. So basically you do some transformation, okay, and you have the new axis. And then the new axis, the data, when you measure the data along this new axis, it will spread out the most, okay. And we can basically take a look at the previous slides. No, not this one. Yeah, for this one. Is that if you take a look like this, regarding the spread out of the data, is it? So that's why the highest, the maximum variance, is it? So it's spread out, you can clearly see along this direction, is it? The data spread out. Because you compare versus the vertical or horizontal, is it? This new axis, data on this new axis spread out more, is it? So that's why we say this is the principal component, okay. Okay, so that's regarding the concept we discussed, okay. So next, let's see another diagram, okay. My notes. So PCA, okay, so here I'm trying to explain, is it? Because the PCA, as previously we saw, is it? It attempts to find the orthogonal component axis. This axis, and then the variance is maxima. Is it? So that means it's spread out the most. Is it? And in this diagram, we can also see, is it? So you have this of this kind of data samples, is it cross? And we also have circle ones, is it? Circle one. And we also have square kind of data, is it? And so this is along the original feature space, is it? So X1 and X2, original feature space, is it? And with their kind of scaled value, is it, for the features, okay? And then over here, we can say, okay, so we have these two new axes, is it? And the orthogonal, is it? The two new one also orthogonal to each other, is it? U1 and U2, is it? And you can kind of see, is it? Along this U1, is it? Data spread out the most. Is it? Data spread out the most. Is it spread out more? And then if you kind of project the data to this new axis, is it? And it's kind of easier classify, compare with you project the data, is it, into X1. Is it? Because it's more spread out. So for different class of samples, then they are more separable. Is it? Versus you see over here, is it? It's kind of crumble together. But if you spread, if you project onto this axis, then it's more separable, because it's spread out more. So this explains the concept of PCA, okay, to find the maximum variance, okay, along the component axis, okay. So here's as a kind of you reduce from x1, x2 two feature space to one dimension, that U1 dimension, and here it also explains why U1 is better than U2, because what? Because sample to U1's distance more close enough, okay, and also it's more separable, okay. So let's go back to take a look the diagram. So you have this two, new axis, U1, and U2, and why we choose U1 not U2, that's because one is it's more spread out, the other one is if you take a look, the distance, between the samples and this axis, it's smaller, versus you project, you see this one, if you project to U2, then this distance is larger than you project to U1, so that's why we pick U1, okay, U1 is better than U2, okay. Okay, so here it explains kind of geometrically we can see the concept. Okay, and then next is, previously we mentioned the correlation, between features. And how do we measure it? Here it says we can use some covariance between two features, x1 and x2, okay. Xj and xk are two features, okay, two features. And what is the covariance? Then we can express the covariance between this xj and xk feature as sigma jk, okay. So samples j's feature, so this is regarding all samples, okay, and it's j's feature, and this is what? This is mean of all samples j feature, okay, and times the k's feature, and the mean of all samples of k feature, okay, so that's mu j, mu k is constant. So then if you have this represents the covariance, okay, between these two features, okay, and the covariance matrix, then we can express it like this, because you have, if you have d features here, okay, so the number of feature is d, okay, and then the covariance matrix is going to be d by d, okay, it's going to be d by d, and along the diagonal, it's the specific features square, okay, it's always the features square, okay, and then the row and the column is determined by, so this is the first feature and the d features covariance, okay. So first row represent the covariance between the first feature and all of the other features. The second row then represents the covariance between the second feature and all of the other features. Okay, so it represents this kind of relationship. Okay, and once you know this covariance matrix, that's what we needed to use to derive the principal component, okay, the PCA concept, okay. So with this, okay, with that covariance, so this is that covariance matrix. So here I'm trying to explain briefly about the math background. Okay, it's much more complicated. So here is the major point. Okay, covariance matrix is this sigma, is it? And this is, we call it an eigenvector. Okay, eigenvector. And I believe it's a content from linear algebra, okay, class. So it's eigenvector, is it? And lambda is the eigenvalue, is it? So if you have some matrix, is it? And you can find some eigenvector, is it? Make it equal to some eigenvalue, okay, scalar times the vector. Okay, so that's the point. Okay, so here we have the concept of eigenvector and eigenvalue. Okay, and then it says eigenvector of the covariance matrix represent the principal components. Okay, so the direction of maximum variance. As to why, this is some complicated math background. Okay, if you're interested, you can find it from linear algebra. So anyway, so the principle, the component basic is just the eigenvectors of the covariance matrix. Okay, covariance matrix. As the eigenvalue then defines their magnitude. Okay, define their magnitude. Okay, and how do we pick the principal components? Is it informative eigenvectors? Is it? Here says we are going to use total and explained variance to select the number of k. Because original, this is original, D is original number of features, okay? And we want to reduce from original k dimension space, feature space, is it, to what? To k dimension feature space. Is it? That's our goal. So then, of course, you need to pick the most important k eigenvectors. Is it? How do we do that? We can use eigenvalues to pick. Okay, we can use eigenvalue. So it depends. Is it certain percentage of variance you want to retain to keep it? The variance, is it? So it says, okay, I want to keep 99% of variance, is it? Then what you can do is, so this is the sum of all eigenvalues, is it? And then you can try, is it, with from the first all the way to the k. If it's approach 99%, is it? Then you say, okay, I'm going to keep this k number. Okay, that's how PCA works. Okay, the working mechanism behind it. Okay, to select the number of principal components, because if you still keep the original D, then it didn't achieve the dimensionality reduction, is that? So that's why over here we said, and this as a variance. Okay, we already know variance measures, is that? And once you find out the key number of eigenvectors, is that? So these are key eigenvectors. Is it basically it's our feature space, new feature space. Is it new feature? So you can have this matrix. Is it? And what is this matrix? This is the transformation matrix. Okay, the projection matrix. So projection matrix is built upon with all of the eigenvectors that you choose. Okay. Okay, then next, let's see. So how do we do the transform? Is it for a sample, like over here it says, the sample is how do we transform? Is it, and once you have this projection matrix, this is the original feature, is it? So you just use original feature times the projection matrix, then you will get the new feature. So this then is the sample on the new feature space. Okay, new feature space. Okay, so this is the working mechanism behind the PCA. Okay, we kind of need to understand it. And next is advice for applying PCA. So because it can achieve dimensionality reduction, so it can be used to achieve compression, okay? So we can reduce memory or disk needed to store data, okay? We can also speed up learning algorithm, okay? And also it's for visualization, okay? We can also see from our previous diagram that, so that's two of the two of the places that we can use quite frequently. And this says it's not recommended use PCA to prevent overfitting. Okay, so keep this in mind. So do not use PCA. Okay. No PCA for overfitting, prevent overfitting. Okay, to prevent overfitting, L2 is recommended. Okay, and L1 can also achieve the goal for feature selection. So that's what we learned before. Okay, and then next, let's take a look at the example to have better understand of it, how PCA works. Okay, so here, let's see. So we are going to apply PCA and logistic regression, okay, on what? On the MNIST data. And previously, I remember we kind of discussed the MNIST data, is it? So MNIST is a database of handwritten digits. So 0, 1, 2, 2, 9. Okay, so the 10-digit handwritten, is it? And each is stored as an image. And how do we make a machine? Is it next time if like I wrote this 9, is it? And if you have a certain application, it can recognize it's 9, is it? So how do we do the digit recognition, the image recognition, the most basic one, okay? And because of it's a single digit recognition, so the class we have 10, is it? 10 class. And total sample is 7,000. No, total sample is 70,000. Okay, 70,000. And each class, so each digit, we have 7,000. Okay, so, and the dimensionality here says it's 784. How do we achieve this? It's 32 by 32 pixels. Okay, pixels. And then it's dimensionality, as it's total feature is 784. Okay, 784. And the value, each of it, because it's a pixel, is it? So it's a color. So it's from 0 to 255. Okay. So this is the general feature about the data set. Okay, data set. And over here, to use PCA, we import from sklearn decomposition. Okay, then you can import PCA. And standard scalar we already learned. Is it to load MNIST data, sklearn data sets also provide that you can just import the fetch ML data. Okay. So over here, so then let's see. That so over here is that we first load the data, MNIST data. Is that and it we already know a total it has 70,000 rows. Is it and how many columns? Rows. How many columns? 784 columns. Is it columns? Is it 784? Because it's 32 by 32. Is it you flatten it? Okay, so that's so the shape we know. Is it? And we are going to do split. Okay, so we are going to do 1/3. Okay, splitting. So the training image. Okay, we know this. So we are going to have 60,000 for training. Okay, and then we are going to have 10,000 for testing. Is it? So let's take a look. Is it? What's the original data looks like? Is it? So over here. So from the original, so over here we try to get the first 5 samples. Okay, we want to draw it. Is it? And their label we so the corresponding digit is a corresponding digit. Okay, so this is its training data. Is it? So we do zip and enumerate. Is it? Then we can get the corresponding index, the image, and the label. Is it? And because over here we want to show the image. Oh, I remember it's wrong. So the dimension is 28 by 28 pixels. Is it? Over here you can see. Is it? It's 25 and 28 here. Is it? And the 28 here. And that so it's 28 by 28 pixels. So this image, this one, is it? It's 784. Is it? So, but this is a flattened one. Flattened one. Is it? And if you want to really see the digit, is it? You need to get it back to its 2-dimensional. It's 28 by 28. Is it? And here color map, we are going to use gray color. Is it? And so over here you can see each of the digit. Is it? And this is their corresponding label. Is it? The class. Okay. So that's image. Is it? Okay, and you may also be interested what it looks like. Is it? So here it also gave us, is it? This is the second number. The second number is 1, is it, from the previous. So what it really looks like, it's 28 by 28. You can see it's a lot of zeros, is it? And it's between 0 to 255, is it? And over here, it's so all of this just represents at that specific pixel, is it what color it's going to be, is it? And because over here, if you can display it in row by row, is it? And it will clearly reflect it as this one. Okay, so that's the decomposing of the original data. And what next it says, I'm going to try to find the 95% of explained variance. Okay, so with the PCA, it's pretty simple. Is that you just call the PCA constructor, is it, to create the PCA object. And here you specify, I want 95% of explained variance. Is it? So once this done, then you can do fit. Is it just like what previously we learned? Is it for all of the models you need to do fit? Is it? And then over here, is it if you want to know how many principal components it contains, then you can call n components. Over here it shows it's 154. Is it? So you can see your previously it's your number of features 784. Now it's decreased to 154. Is it? So it's much smaller. Is it? It's much smaller. So that's why we say it's kind of, you can compress the representation. Is it? You can compress the representation. Is it kind of like image compression? Is it? Okay, then next let's see. Okay, then you're going to apply the PCA on our training data. Is it on our training data? And over here, we also want to kind of, because we want to get back to the original data so that we will be able to see, is it? So that's why you can call PCA inverse transform. Is it? With these components, then it will bring back to an approximation of the original high dimensional data. Okay, so that you will be able to see. So then let's see, is it? So over here, is it? So in this diagram, it draw, this part draw the original image, is it? And what this part is using our transformed data, is it? Approximation, is it? The compressed, is it? Data to show the image. Is it? You can clearly see, is it? You can still see it's full, is it? But regarding its clearliness, is it? So it's not as clear as the original, is it? But you can still kind of see it, is it? With the reduced number of features, is it? And this maintain 95% of explained variance, is it? So even though the image quality, is it? Image quality decrease a little, is it? But we can still see it, is it? So that's why, so it depends on if you want a high quality image or low quality image, is it? So that's over here to explain the concept of compression, is it? Dimension compression. And the next, okay, we use the PCA, is it? And if you don't specify the percentage of the explained variance, is it? It will be the original, is it? It won't decrease, okay. And what over next part is try to show the explained variance, the summation of the explained variance. Okay, so you can get all the explained variance and you sum them up. Okay, then you get the total. Okay, get the total. Okay, so and then what next one try to show is then you can arrange the explained variance, is that you can sort it, is it? Sort it. And then you can just kind of output it, and here it lists the top 5, is it? Top 5, and it's percentage, is it? It's percentage, okay, variance explained, is it? So you get, okay, the first component, second component, is it? It's kind of its importance, and you can clearly see is it's decreasing, is it? Okay. So that's gave us the explain variance, is it? And we do sorting. And what the next one try to show us, is it? Is about the cumulative, okay, the cumulative explained, variance. So cumulative, it's based on you consider one principal component, two principal, three component principal, is it over here is 200 principal components, is it? And the cumulative explained variance value, is it? Percentage, is it? And you can kind of see when this diagram reaches around 200, is it? It's already kind of reach the percentage, 100%, is it? Later on, if you add more principal component, it won't increase this value, is it? And this three line also explain the 95%, 90%, 85% explain variance. Okay, so it's just to try to show. So if you just wanted to get like 85% explain variance, is it? So then the number of principal components then you can pick is what? Maybe it's around 70-ish. Is it like over here? Is it? And if you want to get 90% of explain variance, then the number of principal component you need to pick maybe 90, is it? So something like this. So it will help you determine the number of principal components, okay? And of course, it also explained its performance later on, okay, with the number of the principal components you pick. Okay, and we run out of time today. So today we didn't get a chance to complete all of them. So tomorrow we will try to finish PCA, okay. Any other questions? If there is no questions, then bye and see you tomorrow.
Bye, thank you.